Good evening and welcome to the Menil collection. My name is Carl Killian. I'm the Director of Public Programs here. And when I ask you, if you please turn off your cell phones. We're here tonight to hear about a work of art called The Infinity Machine, created by Canadian artists Janet Cardiff and George Bures Miller. It is the first in an experimental series of year-long site-specific installations in the former Byzantine Fresco Chapel at the Menil collection. Those of you who have visited know that the Infinity Machine contains 150 whirling mirrors, a beautiful light program, and a soundtrack recorded in space by NASA. These are sights and sounds that relate to a theory of the universe espoused by Pythagoras, a 6th century BC Greek philosopher who 9,000 years ago had an idea he called the music of the spheres. Our speakers tonight are both professors at Rice University. One's a classicist, one's an astronomer, and they'll talk selectively, take us through those centuries between Pythagoras and today. Scott McGill, chairman of the Rice Classical and European Studies Department, will use the work of other preeminent Greek and Roman writers to help create the world of Pythagoras. Astronomer Christopher M. Johns-Krull, professor in Rice's Department of Physics and Astronomy, will, after taking a brief look at the contributions of the 17th century astronomer physicist Johannes Kepler, move the story forward to NASA and the Voyager missions. The Infinity Machine was curated by Toby Camps, Menil Collection Curator of Modern and Contemporary Art, and is generously supported by the City of Houston. Scott McGill received both an MA and a PhD from Yale University. He teaches courses in Latin language and literature and Roman culture at Rice, where he became the chair of the Classical and European Studies Department in 2014. The author of a book on Virgil, he's currently working on an edited volume of essays on late antiquity and a book on plagiarism in classical literature. Christopher Johns-Krull attended the University of Texas at Austin and was awarded an MA and a PhD from the University of California at Berkeley. Since 2001, he's taught in the Department of Physics and Astronomy. An active scholar, his list of publications fills 21 pages of single-space typing. Please help me to welcome Scott McGill and Chris Johnson.
Hi there. I'm Scott McGill. I want to thank, first of all, the Menil for inviting me to speak tonight, and Carl in particular. Now, I have to say I'm a classicist by trade, Latin and Greek, so I'm not used to speaking in front of so many people. Right? Usually our classes aren't quite this big, but I'm excited about it and certainly looking forward to it. And looking forward to telling you a bit about Pythagoras, the person with whom the idea of the music of the spheres originated. So I thought tonight, in the time I have, I would tell you a bit about him, about his biography, and then lead you to some ideas about music that originated with him, and then talk about the music of the spheres themselves, okay, and his ideas about them. So, as Carl said, Pythagoras is a 6th century Greek philosopher. So he's born probably around 570 BC. Now I say probably, you'll hear the words probably and perhaps quite a bit tonight because there's very little, well, the evidence for him is not altogether rock solid. Okay, so we have a lot of sources on him, but we have no writings from him. Okay, nothing survives from him. There are some forgeries, but nothing from him himself. One of the reasons for this is because it would appear when he taught only orally. So you will have sources from antiquity, when they're citing Pythagoras, will use the Greek autos ephe, which means the man himself said. right? But saying is the important thing there, not the man himself wrote. Okay, so we don't have, as I said, any firsthand primary material from Pythagoras. We do have a lot of sources who talk about him, and this is because his life fascinated the ancients as I think it fascinates, oops, this moves, as it fascinates the moderns as well. Okay, so let me move this just a little. So this is a bust of Pythagoras in the Capitoline Museum. Now, Pythagoras, what fascinates, I think, the ancient sources about him is his kind of superhuman qualities and his, according to the sources, kind of quasi-divine qualities. These characteristics of him are present in the stories surrounding his birth. So in the most common story that we hear, and this comes from a later biographer named Iamblichus. Don't be kind of embarrassed if you don't know him. Most classicists don't know him, so don't worry. He's roughly 245 to 325 AD, so he's writing long after Pythagoras' own life. But in this story that came down to Iamblichus, Pythagoras' father goes to the oracle at Delphi, and the oracle predicts that his wife will bring forth a son who is supremely beautiful, wise, and good to mankind. Okay, and then Pythagoras is named after the Pythian Apollo. The Pythian Apollo, this is the oracle at Delphi, so this is why he has the name Pythagoras. But even connected to his birth, you have this sense that this is a figure who's, you know, somewhat more, right, than your common mortal. He's born in Samos. I think I have a slide here. So circled in red. So this is Greece, right? And it's on the eastern shore of the Aegean. Okay. He leaves Samos at 18, our sources tell us. There was a tyrant there named Polycrates who, in some way, the sources tell us, compelled Pythagoras to leave the island. Pythagoras felt that he might receive some impediment to his study. The sources are a bit vague about this, but under this tyrant, Pythagoras felt the need to leave Samos. And he began to travel, and during his travels, he studied. And the first person with whom he studied was Thales. Thales is one of the 7 wise men of ancient Greece. He's known to be the first philosopher in ancient Greece, and this is because he tried to explain the world without recourse to mythology. He tried to explain natural phenomena naturally, not in relation to the gods. Okay? So Pythagoras goes to study with Thales. Thales is, again, one of the 7 wise men of Greece. He's great original thinker. And what does Thales think about Pythagoras? He thinks that Pythagoras is really special, right? More special than Thales himself, that he has a kind of intellect that Thales can kind of only imagine having. So even with that story, we see there too this precocious Pythagoras, right? And this Pythagoras who is, again, something greater, right? Something kind of, again, in touch with some higher forces. Okay, so he acquires knowledge with Thales. He shows great talent. Oh yes, I have a slide on this as well. Oh, this is a bit out of order. I'll come back to that in a second. So a later poet named Ovid, you might have heard of him. He is a Roman poet from late 1st century BC, early 1st century AD. In his poem, The Metamorphoses, he writes about Pythagoras. Okay, in book 15 of the Metamorphoses, it's Pythagoras' vision of how the world works. Okay, and Ovid, to introduce Pythagoras, he writes this: "A man lived here, a Samian by birth, but he had fled from Samos and its masters, and hating tyranny by his own choice became an exile. Though the gods in heaven lived far removed, he approached them in his mind, and things that nature kept from mortal sight his inward eye explored." Okay, this is the way he's understood, right? He approached the gods in his mind, right? things kept from mortal sight. He's something more than mortal. His inward eye, right, he's able to see. He's able to explore and to approach. As part of his education, then he studies with Thales, and then he moves to the east. He goes to Babylon for a while, and he goes to Egypt. Okay, Egypt first, actually, and then Babylon. In both places, he learns geometry, he learns astronomy, and he learns music. Okay, our sources tell us that this is where he acquires his scientific and musical knowledge, okay, during his travels to the east. He then goes back to Samos. He's 56 years old by this point. He had studied in Egypt, our sources tell us, for 22 years, and in Babylon for 12. Makes his way back to Samos, but then decides to go, and I'll go back here, to Croton, which is in the south of Italy, in what was called Magna Graecia, because the Greeks had colonized that part of Italy in this period of ancient history. He goes there, our sources tell us, because he claims all philosophers live abroad, and demands at home are too great. Here's the notion again that Samos kind of can't contain him. And he feels that there are learned men in Italy in abundance. So he settles here in the south, as I said, in the south of Italy, Magna Graecia. When he settles there, he forms some kind of community. Okay? Another biographer named Diogenes Laertius says he forms a brotherhood or a club. Okay? In this club or brotherhood or school, we can maybe call it, there are secret practices, some esoteric rites involving science and mathematics, and maybe the worship of Apollo as well. There's moral instruction in this community. There's a strict code of conduct. Okay? It was possibly a school. Okay, but we can't be sure what that would mean. Some sources tell us that there were teachers and listeners. That would certainly imply a school. Other sources are a little less clear about that. I think we can say that it's somewhere between a school and a cult. Okay, and a cult not in the negative kind of let's all wear the same sneakers and wait for the mothership kind of cult. Not like that, thankfully. A cult, the word cult in antiquity meant something different. It meant a kind of private circle of knowledge. Okay, some people had access to this kind of knowledge, others didn't. Those who did were in the cult, and those who didn't were not. Okay, so I think we can understand what Pythagoras' community, using the word cult, but understanding it, I think, differently from how we do today. Now, certainly, too, there was a bit of a cult of personality around Pythagoras. There's certainly that as well. Okay, and I've got a nice passage here from Iamblichus about how Pythagoras was received in Italy. Okay, and the kind of fanfare that he received. So I'll just read this out to you. So this great multitude, and these are the people who come to meet Pythagoras when he arrives in Italy, this great multitude of people likewise receiving laws and mandates from Pythagoras as so many divine precepts, and without which they engaged in no occupation, dwelt together with the greatest general concord, celebrated and ranked by their neighbors among the number of the blessed. At the same time, as we have already observed, they shared their possessions in common. Such also was their reverence for Pythagoras that they numbered him with the gods as a certain beneficent and most philanthropic daimon, and daimon here just means kind of divine spirit. Okay, and some indeed celebrated him as the Pythian Apollo, but others considered him the Hyperborean Apollo, another kind of cult manifestation of Apollo. But the thing to take away from this, right, he's treated divinely himself. Okay, so here's that way in which Pythagoras occupies this space between men and gods because of his knowledge, because of his divine wisdom. Okay. A couple of other things about this school or cult, whatever we choose to call it. There was probably vegetarianism. He practiced vegetarianism in this in this community, and Ovid again speaks about this, right? He was the first to ban as food for men the flesh of living things, right? Abstain, preserve your bodies unabused, mortals, with food of sin. How vile a crime that flesh should swallow flesh, body should fatten greedy body, life should live upon the death of other lives. Okay, so we had a sense, right, that this was anathema to him. One reason it was anathema to him is that he believed in metempsychosis, and metempsychosis means the traveling of souls, that when you die, your soul outlives you, and then it comes to occupy another body, okay? So the transmigration of souls is another way of saying this. Some of our sources tell us, one tells us that Pythagoras could remember 4 lives he had lived. Another source, Aulus Gellius, a Roman, states that Pythagoras remembered being a courtesan, right? That must have been a lively conversation when he recounted that. And another source tells us that Pythagoras states that he heard a cry of a friend in the barking of a dog. Okay, so he has a dog, but says, wait a minute, that's a friend of mine, but his soul had left that friend's body and now occupied that of a dog. Now, this means, of course, souls can migrate between species, meaning that they can come to inhabit, well, pigs and cows and things that we eat as meat. So therefore, if you're a meat eater, you're a cannibal in a sense for Pythagoras. Okay, so this is behind some of his thinking here. Okay, of course, one thing I think probably all know Pythagoras for, it's the Pythagorean theorem, a squared plus b squared equals c squared. So put the scientist and will have to help. I'm a humanities person, but I think I'm right about this. If you put a 3 at the A, a 4 at the B, and a 5 at the C, then you've got the Pythagorean theorem, right? So, okay. So we all know him for this. Since antiquity, this theorem was credited to Pythagoras himself. Another mathematical kind of concept associated with him was the tetractys, this is called. This is a triangle with 10, right, the 10 dots. They each form their own triangles. 10 was a perfect number for the Pythagoreans, okay? So these mathematical concepts associated with him. Now, mathematics for Pythagoras, they were associated with religion. Okay, and this is because math reflects the principles of the world for Pythagoras. So Aristotle, in his Metaphysics, says that Pythagoreans thought principles of mathematics were the principles of all things. Math, for Pythagoras, there's a mystic sense of truth that math can reveal, according to Pythagoras. Okay? These ideas possibly come from Orpheus. I'm going to very quickly read you one other section from Iamblichus about this idea. So Iamblichus says, having learnt wisdom from his mother in the mountains, he said that the eternal essence of number is the most providential principle of the universe, of heaven and earth, and the intermediate nature. Okay? And farther still, that it is the root of the permanency of divine natures, of gods and daimons. These are the ideas that Pythagoras worked with as well. Okay, the divinity of math. What Pythagoras is after is that ever elusive thing, and that is the secrets of the universe. Right? He wants to know the secrets of the universe. He wants to know these not through recourse, again, not through recourse to the gods. For him, it's through recourse, especially through mathematics, especially. Okay, not exclusively, but especially. Okay? So this brings us to his ideas about music. Okay. For him, well, the story goes that one day he was passing, and I have this, there's a lot of, yeah, okay. Right, so I have a lot of text here. I'll keep this one up here for a while so you can read it while I speak. He was passing by a blacksmith shop, and he heard the sound of the hammers, and they were all giving off different pitches, and he wanted to figure out why they were giving off these different sounds, okay? And he realized that it had to do with the ratio of the hammers, the size of the hammers. Okay, so one is 2/3 the size of another, one is 1/2 the size of another, and this gave him an idea that the difference in musical pitch had to do with mathematical ratios. okay? So he goes home and he rigs up this contraption, and the story goes on here. Rigs up this contraction with some cords, and he puts weights on the ends of them. He discovers that the cord stretched by the greatest weight produced when compared with that with the smallest weight, produced a sound that's the equivalent of an octave, okay? And then he had these other chords as well, and he realized that, again, the musical interval having to do with these ratios, with the frequency the frequency ratio. So he discovered the perfect fifth, which my musical students tell me is 7 half steps from C to G, and the perfect fourth, which is C to F. Okay, so but he figures these things out, and he figures them out mathematically. Music is also a very important thing to the Pythagoreans. There's a sense in which there's divine expression in music, but it's expressed again because of math, right? Math is at the basis of it. Okay, and that's what's fundamental to the Pythagorean view here. Okay, and then this leads us to the music of the spheres. Okay, and you'll see in this as well. You've got this sense again that he's able to understand things that others can't. He's able to understand ineffable things. He's able to fix his intellect on the sublime, right? Okay, so this is again all that we've seen so far about Pythagoras, also expressed here. The notion of the music of the spheres is that the pitch of notes depends upon the speed of vibrations. Planets move at different rates of motion, and so they must produce a sound, and the sound varies according to the rates of motion. So you have ratios again here at the basis of it. Okay, so he had a notion that the planets did move. It's probable that this idea is not heliocentric. Okay, some sources tell us he had a version of heliocentrism, but certainly the music of the spheres has Earth at the center of things. Okay, but the planets otherwise revolve. As they revolve, they produce pitches, and because of the ways in which these sounds relate to one another, the ratios of them, they produce this harmony. Okay, this harmony. Now, I'll just end here. Here's saying exactly that. I move on to a Roman author named Cicero, again, who might be familiar to some of you. In one of his works on the Republic, De Republica, he has a section devoted called the Dream of Scipio, in which the younger Scipio Aemilianus discovers the elder Scipio Africanus. He has a vision of him from the afterlife, and Scipio Africanus tells Scipio Aemilianus, the younger one, about the music of the spheres. Okay, and you can read it here. What I want to end with here, though, is the next slide. I hope I've kept this up long enough for you to at least get a sense of it. And that is that, right, that men's ears can't hear these things, right? For you, you have no duller sense than that of hearing, but this mighty music produced by the revolution of the whole universe at the highest speed cannot be perceived by human ears any more than you can look straight at the sun, your sense of sight being overpowered by its radiance. Okay, ooh. Oh, okay, that is the end. Okay, never mind, sorry. So, I thought I had one more. Okay, sorry about that. But the idea that Cicero has, and this reflects Pythagorean thinking, is that this music of the spheres is more beautiful than we can imagine. Okay, there's an aesthetic quality to this music that is truly divine, right? But again, it's produced by these physical properties. The universe must be harmonious in this way of thinking. Okay, and this is because I think there's even if it's not with recourse to the gods, there's a sense of the divinity in nature, the divinity in the universe. This must express itself through harmony. Okay, it must express itself through the most beautiful sounds that we can possibly imagine, but that we can't hear. Now, according to the ancients, Pythagoras could hear them, or could at least approach them, could at least conceive of them. Right, and this is what makes Pythagoras the kind of exceptional figure from antiquity. And as we'll hear next, his ideas anticipate in some ways modern science and are at least partly true. And from classical antiquity, that's kind of all we can hope for, I think, so in terms of being confirmed by modern science. So thank you. I'm going to hand the floor over now to Chris.
Okay, well, thank you very much, and I also want to extend my thanks to the Menil and to Carl in particular for arranging this. And so I'm going to take off, not quite where Scott left. We're going to skip a couple thousand years and get to a point where sort of ancient mysticism starts to meet modern science. And that person really is embodied by Johannes Kepler. And shown here is his portrait on the left, and in the top right is a diagram that's supposed to be reminiscent of sort of a Greek understanding of this music of the spheres. And in the bottom right is a model of the universe that Kepler first came up, where he was adopting many of the things that Scott just left us with. But first, let's find out a little bit about Kepler himself. And I picture him up there in the top next to Tycho Brahe, because Brahe was a particularly important person in Kepler's life and also for the history of astronomy. But Kepler himself was born in 1571, died in 1630. Kepler was a mathematician. By all accounts, he was one of the most exceptional mathematicians alive at this time, and so he shared this love of math, this love of numbers, and a sense that there was the divine in numbers with Pythagoras. He studied mathematics at the university in Tübingen, and then assumed a professorship of math in Graz in Austria at age 22. But he was still somewhat of a mystic. Now, he was an astrologer. At the time, kind of like now for scientists, a lot of our funding depends on the government, and the government at that time was not fully reliable in paying him his salary, or at least all of his salary. But he found that he could cast horoscopes for people and supplement his income, and was fairly successful at that. And in some ways, he was probably a more famous astrologer in his day than he was a scientist, at least initially. He then went to work for Tycho in Prague in the year 1600, and shown on the bottom right here is a diagram of an observatory that Tycho had built with funds from the King of Denmark. And what this allowed for Kepler was the best observational data that anybody had ever obtained in the history of the world up to this time. In order to understand how the planets move, you need to know exactly where they are at a given time, and it's a little challenging to make precise measurements with just your naked eye. Telescopes had not been invented yet. Tycho made very large instruments to measure angles, locations, and so forth, and he had an extremely large volume of the most accurate measurements of the positions of the planets that were known at that time. And Kepler thought that if he could examine that data, he would be able to study the true motions of the planets. And there was a problem at that time. It was becoming known that the model that was handed down from antiquity, what we refer to as the geocentric or Ptolemaic model, was very complicated. It had circles on top of circles. The circle was the perfect shape, the perfect geometric shape, so it was assumed that the planets moved in circular paths. And it didn't do such a good job of predicting exactly where the planets were at a given time. And in general, and it also didn't provide any kind of a natural explanation for why some planets like Mercury and Venus can only be seen some certain distance from the sun, whereas other planets can be seen completely on the opposite side of the sky from the sun. And so Copernicus had introduced his heliocentric model, and there was very active debate at the time as to which of these was correct, and the way you could figure it out was to get good data, and Tycho had that data. So Kepler published several books, the Mysterium Cosmographicum, I don't speak Latin, so the Mysteries of the Cosmos in 1597, and that didn't have any of his famous science in it, but it was a connection to the past and a connection to Pythagoras. He developed his what is now called his first law, planetary motion, in 1605, his second law in 1602, and he published those in the New Astronomy in 1609. And he didn't develop his third law until much later in 1618. He had a number of personal and political difficulties, so Kepler was a fairly devout Lutheran, but he didn't actually follow all the precepts of the Lutheran Church, and so sometimes the local Lutheran priest didn't think he was Lutheran enough, and he wouldn't get communion from the Lutheran priest. And then where he was living every now and then was taken over by a new ruler who was Catholic, and he had to move because he was a Lutheran. So he didn't manage to really fit completely in with any of the religious forces that were at play in his particular world. And then in 1619, he published the Harmonies of the Worlds, and he had his laws of planetary motion there, but he also had a lot about the music of the spheres, which is one of the reasons that I'm connecting them here. And then in 1618, 1620, and 1621, he published in a much more readable, basically for the masses type of writing, his thoughts on why the Copernican model of the universe was correct. And that's really kind of what started to spread it more throughout Europe. Okay, so the first book that he published, Kepler was trying to see how you could explain the ordering of the planets through some very simple, pure mathematics. Like Pythagoras, for Kepler, math was divine, and the universe should reflect divinity, and so simple mathematical forms would be examples of that divinity. And so what he believed, now he fully believed in the Copernican model, so he had the sun at the center, but there were, at his time, there were 6 known planets, if you include the Earth as a planet, and passed down from antiquity, there were 5 perfect geometrical solids. So a cube, a tetrahedron, a dodecahedron, and a 12-sided object, a 20-sided object. And so what he tried to figure out is, could you nest one solid inside of another so that the inner solid was just touching the edges of the next solid, and then the sphere that would wrap around the corners of each of those solids would represent where the planets were. And that was the way he tried to order the positions of the planets in the universe. However, this really didn't explain the motions of them very well. And it wasn't until he got a hold of Tycho's data that he could really start to work this out. Now, Tycho, by all accounts, was a bit jealous of Kepler. He knew that Kepler was much more intelligent, at least mathematically, much more skilled mathematically. And so there was this sort of tension there. And apparently, when Kepler first went to work for Brahe, he inadvertently insulted Brahe and a couple of his other assistants. Imagine that, a scientist, mathematician who's socially awkward. Never met one myself. So it took a while for Kepler to actually get a hold of Brahe's data. But once he did, in fact, the first data he got was just on the planet Mars. And so he worked out Mars's orbit. Now again, Kepler is working in a world passed down from the Greeks, basically, of this divine idea that math and geometry can reflect the divine, that the heavens should be divine, and that the circle is the most perfect form. So Kepler tried his best to make the orbit of Mars fit a circle. He tried taking the circle and offsetting it a little bit from the sun. So he didn't think the sun had to be exactly at the center, but the planets had to be moving in a circle. And that still didn't work. He finally hit on the idea of an ellipse, and that is his first law, what he's very famous for, that the planets move around the sun in elliptical paths with the sun at one focus of the ellipse. His second law is that the area, what do I have? I won't try that. That the area swept out by a line connecting to the planet, that planet sweeps out equal areas in equal times. And from that, you derive that the planets move much faster when they are closer to the sun, and they move much more slowly when they are further from the sun. And that is having the orbit be elliptical, not being perfectly circular, means that it's an eccentric orbit. The greater the eccentricity, the more drawn out, the longer that ellipse is. Then later he developed his third law, which was a mathematical relationship between the periods and the average distances of the planets from the sun. And in particular, he found that there was this harmonic or resonant relationships between the orbital speeds of a given planet. Now again, Kepler studied music. Music was one of the four main topics that was studied at this time when Kepler was alive. And so he was very familiar with music. And as Scott mentioned, when things move, they make sounds. It was expected that the planet should make some sort of sound, some sort of music perhaps, when they moved around the sun. And many people had tried to, when the Copernican model first came on, had tried to work out the various sounds that the planets would do and put them into some relationship to their position. Mercury moves around the sun the fastest, so it should maybe have the highest pitched sound. Jupiter and Saturn were the most distant known planets. They move around the sun much more slowly, so they should have perhaps the lowest sounds. But nobody could work out the relative distances to the planets and a sensible musical theme. But what Kepler realized is if you actually look at the speeds, you don't look at the spacing of the planets, but if you look at the speeds that they're moving, what he found is the ratio of the speed that Saturn, for example, moves when it's closest to the sun to when it's furthest from the sun forms a ratio of 4 to 5, which is a major third in music. And so he believed that this was evidence that God had proclaimed that Saturn should be moving and making music within a major third. And so Kepler wrote music for the motions of the planets. Because Mercury is the most eccentric, it has the greatest difference between the closest speed and the furthest speed. It spans the greatest size on the scale. Venus's orbit is almost perfectly circular, so it doesn't have any variation on the scale. It stays the same note the whole time that it's moving. And the other planets fall in where they are. Now, he did say, okay, Jupiter and Saturn are the furthest from the sun, so they are the lowest notes because they're moving around more slowly. And Mercury goes up to the highest notes because it is moving so fast. So now we fast forward to Voyager to connect some of these ideas then to, let me say one other thing about Kepler. Kepler actually tried to have people play this music, and it didn't sound really good. It didn't sound very harmonious at all. and he spent, there are records of his writing. He spent pages and pages and pages trying to work out a musical system for the planets that would sound good. And he couldn't do it. So, and he reasoned that it just made no sense for God to make music in the spheres that nobody could hear and that wouldn't be harmonious to anybody. Now, other people had suggested that if the planets are worlds like the Earth, then they may be inhabited as well. And in fact, Kepler believed that the sun was inhabited, that there were fiery beings on the sun. And if you were going to make music from the planets moving around the sun, perhaps the beings that could hear that music in a harmonious fashion were the ones at the center of all that. So he thought that perhaps this music sounded beautiful to the fiery beings that lived on the sun. So now we fast forward to Voyager to connect to the exhibit that's here at the Menil. So Voyager was a fantastic thing for me. I was not quite a teenager when Voyager was launched, and it truly galvanized my interest in astronomy and is probably, you know, one of the reasons why I do what I do for my career. It was launched in 1977. There were 2 satellites that were launched, and its mission was to visit, their mission were to visit the outer planets, the gas giant planets, Jupiter, Saturn, Uranus, and Neptune, and their moons. They carried with them music of the Earth. There were golden records on each of the satellites. They are not the first satellites to have these records. Pioneer 10 also carried a record as well. Both of these satellites are still functioning. Voyager 1 is about 12 billion miles from the Earth, and Voyager 2 is about 10 billion miles from the Earth. Voyager 1 has passed into interstellar space. It has left the influence of the sun. It has left the influence of the solar system and is now truly in the space between the stars. And Voyager 2 is almost there. It's not quite there, but it's will soon pass out of the solar system completely. So each of the satellites carried these golden records. This is just a small listing of the songs that were on Voyager, on the Voyager records. And it's not just songs. There are greetings in many different languages. There are natural sounds, sound of the wind, sounds in the forest. There's whale sounds. There's many, many things that were put on these records. But some of it was music carried out into the cosmos. So what about the music that you hear when you see the exhibit of the Infinity Machine, or if you were seeing what was playing and listening to it before we started? The music that you're hearing there, the sounds that you're hearing there, are not exactly sounds like we would think of. Sounds for us, sound waves, are waves of pressure that travel through the air in the room, on the Earth. There is some, and that pressure depends on the particles in the air colliding with one another and causing those pressure waves to move out. There are particles in the space around the planets, mainly hydrogen. It's coming from the sun. There's a solar wind that's blowing out from the sun. The very outer layers of the sun are so hot, about 1 million degrees, that the very tenuous outer layers of the sun are flowing away at speeds approaching 1,000 kilometers per second. It's not very dense. And the pressure from that is just not high enough to create sound waves as we understand them. But because it's so hot, the hydrogen that's moving out from the sun is not atoms of hydrogen, but it's ions of hydrogen. It's separate protons and electrons. So they are charged particles. And when charged particles move, they create magnetic fields. And so there are magnetic fields from the sun streaming out into interplanetary space, and the planets, including the outer planets, have their own magnetic field, as does the Earth. And the magnetic field of the planets sort of excludes the magnetic field from the sun, but it's not just a constant, still thing. The stuff that's flowing out from the sun, sometimes it's higher density, sometimes it's lower density, sometimes it's moving a little bit faster, sometimes it's moving a little bit slower. And so it's banging into the magnetic fields of the planets, and the magnetic fields are shaking in response. And one of the things that we see as a consequence of this whole process between the sun and the Earth is the northern lights shown up in the top right, the northern and southern lights. The aurora is created by charged particles trapped in the Earth's magnetic field that get energized by the solar wind. They get energized by the particles coming from the sun. And the outer planets have aurora exactly the same way. Shown in the picture on the bottom left, it is Jupiter. On the bottom right is Saturn. These are from satellites, not Voyager, different satellites that were sent by NASA to these planets. But the bright bluish white rings that you see around the poles of those two planets are the aurora happening on Jupiter and Saturn from exactly the same process that's happening on the Earth. And this is evidence of this, basically the sun banging on the magnetic fields of the Earth and the other planets. And what Voyager detected was those oscillations of the magnetic fields. And those oscillations are in a frequency that's exactly the same as what we hear, the frequencies of sound that we hear on the Earth. And so if you just translate those frequencies and then the amplitudes of that into pressure waves on the Earth, you hear it as sound. And that is the sound that you're hearing when you visit the infinity machine. And we are actually listening for related sounds now from planets around other stars. So shown in the upper right is an image of a relatively nearby star. The star itself is in the center, and the telescope that was used had a coronagraph, basically an occulting disk placed over the star so that it's not so terribly bright, so that you can actually see the planets around it. There are 4 planets that have been detected around this particular star. They are all very massive Jupiter-like planets. The lowest mass one is about 5 times the mass of Jupiter. The highest mass one is about 10 times the mass of Jupiter. So these are giant planets. But we think they should have all the same processes that Jupiter has. They should have magnetic fields, and their stars should be sending out something like the solar wind. These planets, because we can actually see them, happen to be pretty far from their star, but we know of other stars that have Jupiter-like planets that are very close to their star, where the interaction between the winds and the magnetospheres could be very strong. And for example, the Very Large Array, the radio dishes shown in the bottom in New Mexico, have the possibility of detecting this interaction between the stars and the planets. It's actually not quite ready. They're putting some new electronics in those telescopes that will be ready in about 6 months. And one of my colleagues at Rice and I hope to propose to actually try and detect the radio emissions from this process in planets around other stars. Now, going back to resonances, and this was part of what appealed to Kepler so much, there are also, and we mentioned earlier, there are gravitational resonances. When we think of resonances in orbits and in gravitational interactions, if it happens to be that the orbit of an inner planet or moon, what is shown here is for the moons of Jupiter, the 3 of the main moons of Jupiter, if the inner planet, if its orbital period is exactly twice as fast, as the next planet, then when the next one makes 1 orbit, the inner one makes 2. And the point is that they line up in the same place every few orbits, depending on exactly what the resonance is. And so they can interact more strongly with each other gravitationally, and that can perturb things in their orbits. And we see very clear examples of that in the solar system. Shown here on the x-axis, on the bottom axis, is distance from the sun. The units are astronomical units. Those are the Earth-Sun distance. So where it says 2.5, that is 2.5 times the distance from the sun that the Earth is. And in this region of the solar system, there are asteroids. There's the asteroid belt. There's lots of little rocks out there. And shown in the blue lines are resonances with Jupiter. So that inner one at about 2.5, anything there goes around 3 times when Jupiter goes around once. Now, Jupiter is really big, the asteroids are really small, and when their gravitational interaction gets magnified by this resonant process, those asteroids get flung out of those orbits. And that's why you see very few asteroids at these resonant positions, is because Jupiter can easily get rid of them. But the point here is that resonance can shape and is shaping what we see in our solar system. Actually, when we were looking at the picture of Saturn, you may have noticed a gap in its rings. That's another example of this, where one of the moons of Saturn is flinging things in the ring out at that position, creating that gap. We also see examples of resonances where things can be captured. And this is kind of a complicated diagram, but the main thing that I wanted to show, if you can see over towards the left, there's a big circle for Pluto, and there's a bunch of other little circles there, and each of those is a Pluto-like object in the outer solar system. It's a small body that could become a comet if it came into the inner solar system. And there's several of them that happen to be at this particular resonance. It's the resonance of 2 to 3, I think, if I'm reading that correctly, with Neptune. Neptune has captured Pluto into one of these resonance orbits, and it's captured a number of other comet-like things, Pluto-like things into these resonances. So the bottom line is that resonances, which sound beautiful in music, are actually playing a role in the dynamics of our own solar system. In addition to our solar system, we have discovered many stars, in fact, many planets around other stars. The satellite that has done the best job of that was named after Kepler. And all it did was stare at about 160,000 stars. And when a planet happens to pass in front of it, if a planet happens to pass in front of it, that star gets a little bit dimmer while the planet is in front of it, and then it gets bright again. And in this way, the Kepler satellite has discovered about 4,000 planets around other stars. And in some of those stars, there's more than one planet. It's a solar system like our solar system. And we see examples of the periods of those planets in those solar systems interacting in a resonant way, shaping the structure of those solar systems. So these resonances are important throughout the cosmos, it seems. There's other sound-like things in the universe as well. Shown in the top right is a movie of the surface of the sun, and this modeling that's kind of moving around is hot and cold gas rising and falling in the sun. The lighter parts are the hot gas rising, the darker parts are the cold gas falling. But that motion is acting like a hammer hitting the sun. And just like Scott mentioned, the hammer's striking the things that, the iron that Pythagoras heard, and it made him work out his theory of music. These hammers that are hitting the sun are making the sun ring. It is vibrating. Unfortunately, the frequency that it's vibrating at is much less than 1 hertz, so we would not be able to hear it. If you translated that to a sound wave, we wouldn't be able to hear it. But there's also other places in the universe where we see pressure waves, and again, sound is just pressure waves moving out. There's a galaxy on the left here that has a black hole that is spinning, and it is sending pressure waves through the gas around it. And now the pressure waves are very, very, very low frequency. The New York Times article advertised it as the lowest note in the universe. It's about 57 octaves below middle C. Really low. We couldn't hear it either. So then moving on to the infinity machine, we've talked about the sounds, but for me, when I saw it, it was the mirrors that appealed to me the most. Because I'm an astronomer that uses telescopes. Mirrors are the heart of telescopes, of optical and infrared telescopes. All the telescopes I use, the heart of that is a mirror. So I was fascinated by the mirrors. The infinity machine has two mirrors right at the center facing each other, giving you an infinite series of reflections, kind of shown in the example of the picture in the top right. And I take it that's kind of where it gets its name. I was hoping that there would be a telescope mirror somewhere in the infinity machine. Apparently there isn't. But that's my own personal bias. But for me, the telescopes allow us to stretch our vision and our imagination almost to infinity, to the edge of the universe. It's not quite infinitely far away, but it's quite far away, 13.8 billion light years. So I was fascinated by the infinity machine. Didn't quite see the mirror I was looking for, and I'll leave you with that.
So I think at this point we're supposed to field any questions that the audience might have.
You talked about Kepler's musical translation of the motion of the planets, and how Kepler had his idea of the movement of the planets translated to music, and that was played back and was not beautiful. And I personally think, and I think many people would agree, that the sounds that we hear in the infinity machine, the solar winds hitting the magnetic spheres of the different moons and planets in our solar system, are beautiful. Can you account from that from either of your disciplines, or do you think that's just a kind of coincidence?
I think that's your answer.
So I haven't actually played the music that Kepler wrote. If you played each one individually, it might actually be pretty harmonious. It was putting them all together. And all the planets are moving simultaneously, so Kepler imagined that you had to play them all together. And he couldn't make that harmonious. And so if you put all the music in the infinity machine together at the same time, I don't know what it would sound like, but it may not sound harmonious. We should try it.
Given that the orbits are not circular, but they're elliptical, what kind of effect would you have by evokes? Given that the orbits are not circular, but they're elliptical, what kind of a phase effect do you think there would be as they kind of change in their relationship?
Within one planet or within each other? So that's part of those resonant interactions from the gravitational thing, because if they become eccentric, if they are in a resonance with another planet, and we see this in the extrasolar planets, the interaction makes them more eccentric, and if they get more eccentric, that kind of reinforces their interactions, and in some cases, it can cause one of them to be flung out. Usually it's the lower mass one, so the high mass one is the big bully, he gets to stick around, and the little guy gets shot out somewhere. Sometimes it gets shot out, sometimes it gets shot in towards its star and gets destroyed.
So what does that do to the actual sounds from translating the magnetic wind to the auditory representation?
So the closer you are to the star, the bigger the interaction is, so that would probably make the sounds louder and kind of changing in frequency more rapidly. So maybe that's the death scream of the planet as it gets flung into its star.
It's always seemed something of an interesting coincidence that the human language we call mathematics correlates so well with the physical world. And I've often wondered if there is a philosophy or some sort of in-depth understanding as to why that correlation came about.
I myself study poetry, so it's difficult for me to answer that myself. But certainly, this was exactly the question I think that Pythagoras was hoping to answer, and I think it's a kind of eternal human question, right? Why does math work so well, right, in explaining a lot of these things? So, and I think for Pythagoras, to get at that understanding was to get at the understanding of all things. Now, for me, what's always interesting, again, as a humanist, is the search itself, and the impulse itself that drove Pythagoras and others, 2,500 years ago, and continues to, right? So I have no answer for that, but I'm certainly I certainly feel that your question is exactly the motivation that Pythagoras had, right? So it's thinking along the same terms, the same lines rather.
So each of you might have a different response to this, but what is so divine about spheres and circles? That's something that I've always wondered.
So it's my understanding, as the tradition was passed down from the ancients, that the fact that the circle has no beginning or end is kind of what makes it perfect in some sense, and so that's probably my best guess at that.
I think that's right. Yeah, I'm more partial to the trapezoid myself, but that's just me.
I think that there's some in the back over here. Very back.
Just a simple question for a science update. Are we still receiving signals from Voyager 1 and 2?
Yes, we're still receiving information back from them. There are a number of questions about exactly how the solar wind interacts with the gas between the stars, the interstellar medium, and so we are still receiving data from it. We don't receive data on a daily basis because it's hard to see those signals, and the radio telescopes that are capable of doing that have to communicate with a bunch of other satellites as well. So it's not a daily update, but we do get information back from them.
Yes, we heard about Pythagoras that could see what the gods saw and had this kind of inner vision. And seeing the harmony on the planets that brings us to the physical laws. I could not avoid thinking about Bohr's atom, right, where the allowed orbits for the electron are the ones that are in resonance with the wavelength of the electron itself, being a particle and a wave. What is your take about this ability of certain people on the Greek tradition that somehow are able to make this kind of insights that brings us to the very modern and recent science?
Yeah, it's certainly remarkable, and I think it was remarkable for the ancients as well, and that's why Pythagoras was understood as he was and treated as he was, right? That he did in fact have this unusual, almost second sight, right? And there are others as well. Archimedes is a good example of this, I think, from the Greek world. So, you know, how the instincts were so right? And that's what's so interesting. And again, how they were to arrive at it, the ancients themselves couldn't explain it, and that's why they have recourse to, well, when his father went to Delphi, he was told that in fact you're going to have this exceptional son. So they had to explain it. They had to kind of mystify it. Right? So for them too, it was extraordinary and difficult to account for.
With a different composition or quality or density of atmosphere on a different planet, would the music sound different if we were listening to it on Venus?
Almost certainly it would. And so in that sense, Kepler was correct that the music would probably sound different on the different planets. Now, not all of them have atmospheres that would really translate that. And the sun has no surface, so you have to pick exactly where you want to sit in the sun. And I don't recommend doing that. But so yes, there would be different, the sound would be perceived differently on the different planets.
I'd like to find the planet where it sounds like the Star Wars theme, right? That could be pretty great.
That's the right word. Okay.
Hi. Given Pythagoras' fascination with ratios, what was his interest, if any, in the golden ratio that's found in nature? If you can speak to that.
You know what? I don't know, to be honest. I would have to look that up. But if I can certainly do so if you want to stay afterward and give me your email address, and I could let you know. Yeah.
I thought that I read something in the article about it, this talk, that there was going to be a discussion of 440, the concert A, the major tone that we use when we're tuning our instruments. And I'm wondering if you could speak to that.
I don't know about that. They didn't tell us.
Hi. My question might be something I should have Googled first, but this is an easier way to get an answer. I know that you're working on studying the magnetic fields and like how they interact with various planets. I was wondering, how do the solar winds actually travel through a vacuum, and is the magnetic field like just around a planet to a certain extent, or does it like permeate through space?
So wind is an analogy term. It's not exactly wind blowing in the way we think of the winds on the Earth. It is what is happening is the outer layers of the sun are heated to very high temperatures. We don't actually fully understand how that happens. We are pretty certain it has something to do with the sun's magnetic field. But what we do know is that there is this corona surrounding the sun that's about 1.5 to 2 million degrees. And what we perceive as temperature is random motion of particles in a gas. They're moving at some speed. And so at that very high temperature, some of those particles are moving faster than the escape velocity of the sun. So the ones that are moving that fast that happen to be directed away from the sun escape. They just are moving out and they keep going because the sun's gravity is not strong enough to hold them back. And because they are charged, because they are individual protons and electrons, any moving charge creates a magnetic field, and that field goes along with the motion of the particles. So as the particles move away from the sun, they are carrying the magnetic field with them.
How does that come about? How does the magnetic field of a planet or a moon come about?
So in the Earth, for example, the core of the Earth is molten. It's warm. And so there are ionized atoms there. There's free charges. There's protons and electrons there. And because the Earth is spinning, those charged particles are moving more or less in a circular, and particles that move in a charges that move in a circle create that classical dipole magnetic field that we saw in the pictures.
I think we can take one more question.
Hi. I was reading a few things about trying to grasp things like general relativity and quantum mechanics, and things about, I don't know, I feel like science started exploring the world that we know through the senses, which seems to be physical material, but it seems to be becoming reduced into something more abstract that I can't really grasp with my like hands, my senses. But I don't know, is this similar to what Pythagoras was trying to figure out? I guess the world that modern scientists understand, it seems to become more abstract.
Well, I would say in one way it was less abstract, right? Because he and other early philosophers, and Pythagoras is an early philosopher, so 6th century is the period of when philosophy originates, and we understand philosophy again as trying to understand especially the natural world without recourse to the gods, right? So in that way, you're actually trying to demystify things, right? Philosophy is also interested very much in ethics, in human relationships and social organizations, but that's a separate branch of it from what we're talking about now. So in that way, I think it's more concrete, or at least more less mysterious, at least, right? But then within that, because obviously there was not nearly the kind of understanding of how things work and the kinds of instruments that we have today, the concrete knowledge he's trying to get at it through mathematical theory, right? So, so I think it's kind of somewhere between the two, where it's theoretical in the math, but nonetheless, just the very move, the revolutionary move from ascribing things to divinity to trying to understand them on their own terms, that's of course a move away from the abstract. So,
and I would just add, yes, that I think it shares that reliance on math. Now, exactly why math works so well to describe nature is I think a question that's really kind of hard to answer. It does. You mentioned quantum mechanics, and so that's developed out of very straightforward, somewhat hard to do, but sensible mathematics, and it makes predictions that we have to be able to observe, and we do make those observations. What is fascinating and I think very, very hard to sometimes grasp is those theories have told us that at the very small level, the level of the atom that was mentioned earlier, things in nature become fuzzy. There are no longer hard things. Nature becomes very, very fuzzy. But that just seems to be the way nature is.
Thank you so much.